Hi everyone. In this video we're going to be talking about monitoring the conditions in the Haber process. Okay, so looking at the fact that Le Chatelier's principle and equilibrium concepts help us to understand how we need to design this process in order to get maximum yield, a maximum rate, and minimum cost, which is essentially the goal here. Okay, so first of all, we're going to talk about compromise conditions, what we call compromise conditions, and how we set up the Haber process, and then we're going to talk about what we actually monitor in the showing you a bit of a schematic of the process. Okay, so when we're thinking about compromise conditions, what we're trying to identify there is we're trying to think about, knowing what we know about Le Chatelier's principle and this equilibrium, how do we set up this equilibrium so that we get the best possible outcome? Okay, so what we're going to consider there is we're going to first of all look at temperature. Okay, so I'm just going to write a few kind of quick summary notes in this sort of spot, so bear with me here. So what we know is that low temperature gives the best gives maximum yield, shifts the equilibrium to the right hand side. Okay, we know that because this forward reaction is exothermic, so reaction equals exothermic, shifts equilibrium to the right hand side. What we also know though is that high temp gives maximum rate. Okay, so low temp is basically too slow to be practical, maybe economical, we would say, because ultimately it comes down to, can you make enough stuff in a cost-effective way? Okay, so if low temperature gives us the most yield, but high temperature gives us the fastest rate, okay, then what we do is we end up with moderate temperatures, give the balance between yield and rate. So if we can't, because they work opposite to each other, if we use high temperature, we get fastest, but we get the least. If we use low temperature, we get the most, but it's too slow. If we pick a moderate temperature and somewhere in the middle, we get a good balance between, it's not as much yield as we'd want, and it's not as fast as we want, but it's a good compromise. Okay, so somewhere in the middle. Okay, then what we can say is, all right, well, let's look at it in terms of pressure. So we know that high pressure gives the maximum yield, but okay, so when we use high pressure, we get the maximum yield because we're shifting shifts to the right-hand side. But we know that maintaining high pressure is dangerous and costly. Okay, so low pressure is cheapest and safest, but leads to lower yield. So then what we do, just like with temperature, we do moderate pressures. So if we use a slightly, a pressure that is higher than atmospheric pressure or higher than normal, then we can get a better yield, but at a level that we can maintain a bit more practically. Okay, and so then what we do is we also use a catalyst to lower the necessary temperatures due to lower activation energy. So we can get a better outcome from the temperatures that we do use because we're using the catalyst. So we're using magnetite, which I believe is Fe3O4. Okay, so it uses the iron surface as a way to help break those covalent bonds, to mean that less energy is needed in that bond breaking process. So we get a better outcome. Okay, let's just quickly now move on to think about the monitoring that we do. Okay, so thinking about, all right, well, this is chemical monitoring and management. So what areas of this process do we monitor in order to maintain that things are effective? Okay, so this is a bit of a schematic of the process. All right, so let's see if I can do some different kind of highlighting at points. Okay, there we go. So this would be the first stage that we would monitor. So we're monitoring that we have a stoichiometric mixture. That is a balanced mole ratio mixture of nitrogen and hydrogen gases, 1:3. Okay, so that means that then that we're getting the right combination of reactants. Okay, and then we're monitoring the pump. So remember that we're talking about high pressure of reactant gas. So we're monitoring in the pump to see that the pressure of the gas that we are pumping in is at the right level that we want it. Okay, so what we're talking about here, so we're getting the gas that's kind of pumping in. Okay, so that as this gas kind of comes around the side, the heat of the reaction that's happening in here already starts to warm it up. It goes in here, and then it's being heated up by this element as it makes its way into this chamber. Okay, so we're identifying that we've got a particular pressure, so a higher pressure, so that's around about 250 atmospheres, existing inside here. We've got a particular temperature, so we've got to monitor that as well, and having the catalytic reactor, so the presence of the catalyst inside here for those gas particles to react that way. Okay, and so then the reaction happens, and then the resulting gases are pumped out this way. Okay, so then what we have at this point, we have a combination or a mixture of our ammonia product, but also the unreacted nitrogen and hydrogen gases. So anything that hasn't quite completely reacted during this process obviously gets swept along. But the thing is that we want to make the most of the fact that that's there. So we'll adjust that down here in a minute. Okay, so what happens here is that our gas mixture gets pumped through this coil that's got it's got coolant that goes in that makes this a cold environment. I think at least kind of -30, -40 Celsius. It might be even colder than that. Cold enough that the ammonia, which has a melting point of a boiling point of -33 Celsius, can condense to a liquid. And so then the ammonia, which has condensed to a liquid, drips out the bottom and then can be siphoned out. The nitrogen and hydrogen gases need to be cooled to much lower temperatures before they will condense. So they remain in the gas phase, and so then they are repressurized and pumped back to the reactor so that they're actually pushed back up through here so that we are recycling instead of wasting. Okay, so it's a very smart way to use the process so that we're not spending lots of money on reactant gases that then otherwise get pumped out and wasted. Okay, so we're reusing them. It means that we need to use less of this mixture in order to actually kind of get the reaction going, because we're bringing more recycled reactants back in. Okay, and then we have liquid ammonia at the end that then we can drain out. Okay, but what we also need to monitor is we need to monitor all of the gases and then the product that comes out. So we're monitoring the gases because we want to exclude O2. Okay, so oxygen gas we want to exclude from this process, because what we have oxygen and we have beautifully flammable hydrogen, and we have a high temperature reactor. If you've done the pop test before, you know that hydrogen gas ignites, and it ignites with a whole range of different concentrations of oxygen gas. It will light very, very easily. When it's a stoichiometric mixture with oxygen, it will explode catastrophically. So we want to make sure that there's no oxygen present at any stage of this process. So we monitor carefully to make sure that we have oxygen sensors to check and see that there's no oxygen inside the reaction mixture. We also need to monitor our liquid output to check and see that it is as pure as we can get, that it's not being contaminated by anything else that happens in this process. Okay, because obviously that's going to affect what we can use it for, or perhaps some additional purification steps that we would need to make sure the ammonia is high quality. Okay, so we're monitoring a number of different stages in this process. We're monitoring what goes in, we're monitoring its conditions, we're monitoring what comes out, we're monitoring what we recycle, we're monitoring pressures at various different stages, we're monitoring to ensure there's no contamination from oxygen, which would lead to catastrophic failure, and we're monitoring our products to make sure that what we get at the other end is ideal. Okay, so you can see how important the monitoring is in this process. I've said that word over and over again in the last 30 seconds, more than I care to. So we'll finish the video there. Thanks very much for watching. Bye for now.